right, moving along in our core book to section 10C, sample space and events. In this section, we're going to take a look at what sample spaces are, what events are, and how we can represent them using different methods and use those different methods to help us find probabilities of different events. So the first thing we want to do is get down these definitions. So we have sample space, which takes the letter U for a universal set, is a set of all possible outcomes of an experiment. So if I'm tossing a coin, the sample space is just going to be heads, tails. If I'm rolling a die, the sample space is going to be 1, 2, 3, 4, 5, 6. An event is a set of outcomes in the sample space that have a particular property. So if I'm rolling a die, the event could be rolling a 3. The event could be rolling an even number, rolling a prime number, rolling a number that is a factor of 6. Anything like that could be an event. All right. What we call those values in the sample space are called, we call them elements, okay, elements of the sample space. And when we talk about events, they're subsets of the sample space because they're sets that are made up of the elements in the sample space. Now, we can make a Venn diagram to help us understand the particular outcomes of events, or as we'll see in just a couple of moments here, there are other ways that we can represent these scenarios as well. One more definition before we move on. We see two events are complementary if exactly one of the events must occur. Now that sounds confusing, but basically getting a heads or a tails, if tossing a coin, are considered complementary events because if one doesn't happen, the other one must happen. Okay? If we call event A that it is heads, then A dash or A prime with the apostrophe on top of there is referred to as the complementary event of A or not A. You could say it either way there. Okay, let's take a look at our example. It says a normal six-sided die is rolled once. A is the event that a prime number is rolled. So first, question A says use set notation to list the outcomes in the sample space. So first, we're going to write out U equals. Now, when it refers to set notation, what we have here are these curly braces. Curly brace at the beginning, curly brace at the end, and we have our list of numbers that are in the sample space in this particular sample space. All right. Notice we wrote 1, 2, 3. In this scenario, we can't just write numbers 1 through 6 because that doesn't clearly designate that they must be integers. You could write 1, 2, ... 6 because you've clearly established that you're using only integers, and that's another way to do it. A2 is asking for the outcomes in event A, again, that it is prime. In case you forget the definition of prime, it means that a number has exactly 2 factors. So therefore, the first prime number is 2, and then 3 and 5 are also prime. So A has the elements 2, 3, and 5. 4 and 6 are not prime because they have more than just 2 factors. And A prime, or not A, is just going to be all the elements in the sample space that are not in event A. So if 2, 3, and 5 are in event A, then 1, 4, and 6 are not. And then part B asks us to draw a Venn diagram to illustrate the sample space. We start with a rectangle representing the sample space, and we call that U. Inside, we put the circle representing event A, and the numbers that go inside event A are 2, 3, and 5. And the numbers outside of A, but inside the sample space, are 1, 4, and 6. Now, this is a Venn diagram with only one event in it. Obviously, we'll see many more examples where we have more than one event illustrated in a Venn diagram. Other ways to represent probabilities. We have two-dimensional grids and tree diagrams. Tree diagrams, I feel confident that you've seen before. Two-dimensional grids, maybe you haven't quite seen as often, but they're fairly easy to use. And when do we use them? When we have more than one operation, okay? So it's something along the lines of if I'm rolling 2 die, or if I'm rolling a die and tossing a coin, something along those lines, two-dimensional grids would help us out. So if we look at this example, it says example 4 illustrates the possible outcomes when two coins are tossed using a two-dimensional grid. So what do we see? We see coin 1 on the horizontal axis would be a head or a tail. And over on the vertical axis, we see the same thing. This is coin 2, heads or tails. Each dot that is represented on this two-dimensional grid represents a particular outcome. So what does that mean? That means I could have heads, heads, that would represent this dot here. I could have heads, tails, representing this dot here. This dot over here represents the outcome of tails, heads. Notice I'm saying tails, heads first. I'm saying tails first because that is the outcome of coin 1. And the upper right dot represents tails, tails. If I were doing a tree diagram over here for part B, I first am going to represent coin 1, which has the outcomes heads or tails. And then from each one of those outcomes, I'm going to have another iteration of heads and tails for each one of them. And what are the possible outcomes that are yielded? Well, we could have heads, 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 tails, tails, heads, or tails, tails. Notice we see the same possible outcomes whether we make a two-dimensional grid or a tree diagram. As we'll see later, sometimes the tree diagram is going to be better than the two-dimensional grid and vice versa. But again, it's important to note that the sample space is found in both representations here, in both the two-dimensional grid and in the tree diagram. Let's take a look at example 5 here where we have this spinner. It says use a tree diagram to illustrate the possible outcomes when this spinner is spun 3 times. Well, if we say that it is 3 times, that's why they're telling us to make a tree diagram, because we cannot use a two-dimensional grid to represent something that is happening 3 times. That would obviously require us to use a three-dimensional grid, which becomes more complex than is necessary for a problem like this. So it says use a tree diagram, and then it says highlight the outcomes representing or corresponding to the event obtaining blue twice. All right. So first, let's take a look at what that tree diagram is going to look like. Notice we're going to have a branch for the first, the second, and the third spins. And in each one of these, I've highlighted the outcomes where we end up with 2 blues. So for instance, following the top branch, I go blue, blue, white. That's going to have 2 blues. Or I could go blue, white, blue, also 2 whites. And finally, white, blue, blue. Now, the total number of outcomes here, as you can see, are going to be 8. Blue, 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 white, etc. on down. And only 3 of those instances do we end up seeing 2 blues. All right, and that's going to be important as we move forward to finding probabilities, but we'll hold off on that conversation for now. That's it for section 10C. What we tried to do here, what our objective was to represent sample spaces and events using various methods. We used Venn diagrams, two-dimensional grids, and tree diagrams, and we use these representations to find probabilities. Your assignment for this section, again from the core book, is page 248, numbers 1 through 7. Have a great day.